Hello everyone and welcome to the ninth lecture of the course Calculus and ODEs. In today's lecture we will discuss section 8.9 Taylor and MACLAURIN series from the book Calculus and Analytic Geometry by Thomas and Finney. This section shows how functions that are infinitely differentiable generate power series called Taylor series. Now let's just recall what we did in last section. In last From term by term differentiation theorem, we said that if a power series converges, then it defines a function and that function has derivatives of all orders inside the interval of convergence, right? So we said that the term by term differentiation says that within the interval of convergence I, the sum of a power series is a function with derivatives of all orders defined, right? And since we are saying that derivatives are there, so that function will be a continuous one, right? So whenever you have a power series that is converging in some interval of convergence I, it defines a function and that function has derivatives of all orders, right? Now, what if I say that you have a function which has derivatives of all orders in an interval? Can it be expressed as a power series on at least part of that interval? Right? So we are just going other way around in this one. Earlier we said that if the power series converges, it defines a function which has derivatives of all orders defined. Now we are saying that if you have a function which has derivatives of all orders on an interval I, can it be expressed as a power series? And if it can, what will be its coefficients, right? So let's just answer the second question first, that suppose we assume that it can be expressed as a power series, then we will see that what the coefficients would be, right? So let's just assume, so we are making an assumption here that fx is the sum of a power series about a point x is equal to a, right? And that x is equal to a is a point inside the interval of convergence. Assume that fx is the sum of a power series about x is equal to a. So fx can be written this way, right? This is the meaning that fx is equal to some power series. So fx is equal to a naught plus a1 into x minus a plus a2 into x minus a square, and we keep on going like this. So these are the coefficients ai's which we want to see that what these coefficients would be, right? So we have assumed fx is equal to this with a positive radius of convergence. So we can just apply term by term differentiation theorem here. Just differentiate this term by term within the interval of convergence, right? While writing the term by term differentiation theorem, we said that all ordered derivatives will be defined within the interval of convergence I of the original series, original power series. So f dash x would be a1 plus twice of a2 into x minus a plus thrice of a3 into x minus a whole square up to so on n times an into x minus a to the power n minus 1, and it keeps on going like this. Likewise, you can define f double dash x, that is the second derivative of the function with respect to x. So this one is 0. So this is 2 times a2 into 1 plus 3 times of a3 into twice of x minus a, plus we keep on going like this. And when you go for the third derivative, this term vanishes and you will have 1 into 2 into 3 times a3 plus something. And from here, just look at the trend. You can write the nth derivative as fn of x is equal to, here it was f3, so we had 3 factorial times a3. Now we'll have n factorial times an plus whatever term was left, it had x minus a as a factor. So this plus sum of terms with x minus a as a factor, right? Now we will evaluate the values of these derivatives at this point a. So what is f dash at a? From here you can see that all these terms are not going to contribute. At x is equal to a, all these terms will turn out to be 0. These contribution of these terms, this is also 0. So basically we can say that the first term is going to contribute. So f dash at a is a1, f double dash at a is 2 factorial times a2, and f n at a is n factorial times an. So we can conclude this thing, right? So now we have the value of this coefficient, that a1 is equal to f dash of a2 is equal to f double dash at a divided by 2 factorial, a3 will be f third derivative of f at a divided by 3 factorial, and an will be equal to, so basically we have an is equal to nth derivative of f at point a divided by n factorial, right? So basically these formulas, these f dash, f double dash, f triple dash, these formulas reveal a pattern in the coefficients of any power series, right? We have considered any general power series with coefficients ai's, and we have concluded that ai's should be given by this way, that an is equal to f nth derivative at a divided by n factorial, right? So if f has a series representation, till now we have not answered the question whether it has representation, series representation or not. We just assumed that suppose fx has a series representation, part series representation, in that case the coefficient should turn out to be this one, right? So we are saying that if, still we are writing this if f has a series representation, then it must be of this form. So basically this is a naught, this is a naught plus a1 times of x minus a1 is f dash at a, plus a2 times of x minus a whole square, a2 is f double dash a by 2 factorial. See how we have calculated this a naught, you can just find the function value f at a is equals to a naught. From here you just see, here we wrote the power series here. To get the value of a naught, you just substitute x is equal to a, so all these coefficients will turn out to be 0. So f at a will be equals to a naught, right? That's why we are writing a naught as f of a. So a naught is f of a plus all other ai's are given this way. So this is the series representation of the function f, right? Now let's address the question that when do the Taylor series or the power series representation for the function exist. So let the function f be a function with derivatives of all orders throughout some interval containing a as an interior point, right? So this is the assumption on the function, that f be a function with derivatives of all orders defined throughout in some interval. So if you have this interval I, so throughout this interval the derivative should be defined, and where you have a as an interior point, then you can write the Taylor series generated by this function at this point x is equal to a, right? So what will be the Taylor series generated by f at this point? It is given by f at a plus f dash at a into x minus a plus f double dash at a upon 2 factorial into x minus a whole square, and we keep on going like this, f nth derivative at a divided by n factorial into x minus a to the power n, so which we can represent in the form of this series, right? This summation. And if this a happens to be equal to 0, then we call this Taylor series as the MACLAURIN series. So the MACLAURIN series generated by f is basically a Taylor series generated by f at x is equal to 0. So in place of a, you just write 0 and we have MACLAURIN series, right? So we say that the Taylor series for a function is defined when the function has derivatives of all order throughout some interval containing a as an interior point. So in that case, we can write the function in the form of a Taylor series. We can write a Taylor series generated by that function at some point, right? So let's see an example. Find the Taylor series generated by this function fx is equals to 1 by x at a is equals to t, where if anywhere does the series converge to 1 by x. So basically we have to see that for what values of x this series converge, the Taylor series which we will find out, that series converge to this function 1 by x, right? So we are saying that we have this function, we are writing a Taylor series expansion for this function, and we are also asking that for which values of x this series will actually converge to this function, right? So let's address the first question, that what is the Taylor series generated by this function about this point. So the Taylor series generated by this function at x is equals to 2 is given by summation k going from 0 to infinity kth derivative of f at 2 divided by k factorial into x minus 2 raised to the power k. So we need all the derivatives, first, second, third order defined at 2. So let's see what is fx. Fx is x to the power minus 1. So find value of f at 2. It is 1 by 2. Then what is f dash x? It is minus of x to the power minus 2. Find the value f dash at 2. Likewise, find the second derivative, third derivative, and nth derivative. And you have a trend. So we have fn of x is equals to minus 1 to the power n into n factorial into x to the power minus of n plus 1. And since we need the value of fk at 2 divided by k factorial, so here we are dividing it by 2 factorial, by 3 factorial, by n factorial and getting the values. After this calculation, just plug in the values and find the Taylor series generated by the function at x is equals to 2. So this is the series generated, right? A point to notice here is that whenever you're writing the Taylor series generated by the function, you are just writing the series, you are not putting it equals to f of x. We have not written f of x is equals to this one, right? We do not know whether this series is going to converge to this f of x. We have to check, right? We are saying this is a series, Taylor series generated by this function. Now we will see for which values of x does this series converge to this function. So you see this is a geometric series with common ratio minus of x minus 2 by 2, right? So the first term is 1 by 2 and the common ratio is minus of x minus 2 by 2. Now we want to see that for which values this series is going to converge. This series converges when mod of common ratio is less than 1. That is when mod of x minus 2 by 2 is less than 1, or we can say when mod of x minus 2 is less than 2. In that case, the series converges. Here it is written it converges absolutely. So you can check this series converges absolutely also. When you take absolute, you have plus here, and still the series converges for the same interval, right? So it is written it converges absolutely for this one, but if absolute is there, means the series is going to converge. So we know that absolute convergence implies convergence. So we say that this geometric series converges for these values of x. Means when x lies between 0 to 4, and to which value, to which function it converges? It converges to the sum of the series will be equal to a upon 1 minus r, right? So if it is a upon 1 minus r, it will turn out to be 1 by x. So we can say that the Taylor series generated by this function, it converges to this function for which we have generated the Taylor series for these values of x. Okay. Okay. Now to define Taylor's polynomial, let's first see what is linearization or linear approximation of a function. So see these figures, and suppose you have a function fx is equals to x square. So draw the graph of y is equals to x square. This is represented with this blue curve, y is equals to x square. Now draw a tangent to this curve at this point 1, 1. So you can say that this the line represented by this pink is the tangent whose equation is y is equals to 2x minus 1. You can see the slope of this curve at this point 1, 1, dy by dx is 2x, and at 1, 1 it is 2. So mx plus c, you have minus 1. So this is the tangent and this is the curve, and you see that this is when you have intervals from minus 1 to 3. Now you just try to zoom into this graph and you have this interval from 0 to 2, and this is the tangent and this is the curve, and likewise you keep on zooming and eventually you see here that this line, the tangent line and the function for which you draw the graph, they are just coinciding with each other. So you see the y values along the tangent line are exactly same as the y values on the curve. Or you can say in this case, when you were here, you can see that the points that are lying in the vicinity of 1, the y values for those points on the tangent will give you a very good approximation to the y values on the curve, right? So basically you can approximate this function f of x is equal to x square with this another function which is this defined by this tangent line fx is equal to 2x minus 1 for the points lying near the point where you have drawn the tangent, right? So, and this is for any general curve. We have taken a parabola. You can take any other curve. The phenomena is true not just for parabolas but for every differentiable curve. If you have any curve at for which the tangent can be defined at a point, for that this thing holds that the tangent line is going to give you good approximation to the y values of the curve near the point where you have drawn the tangent, right? So let us just define what is linearization or linear approximation. So if f is a differentiable function if f is differentiable at x is equals to a, so you have this y is equals to f of x. This is the curve and this is the point a comma f of a, and we are saying that the f is differentiable at this point means you can draw this tangent. Then the approximating function is defined by the tangent line. Then the approximating function, which is represented by L of x, which is equal to f of a plus f dash a into x minus a. This is basically the equation of tangent passing through point a comma f of a. This is the linearization of f at a. We call that this function L of x, which is basically defined by the tangent line will be a linear approximation to this function f of x. And this approximation is written as this way, that fx is approximated by L of x. So the approximation of f by L is the standard linear approximation of f at this point a, right? So this is at this point a. The point a is the center of the approximation, right? We are saying that fx is approximated by Lx, and you also need to remember this gives you good approximation in the vicinity of a, right? If you have some point near a, it will give you a good approximation. See, when you go here, they are very much closer. But if you have some point here, in that case, the tangent line and the function value for which you are approximating, they are far away from each other, right? So on this idea, we will define the Taylor's polynomial. The linearization of differentiable function at a point is basically a polynomial of degree 1, which is given by this, which we represented as L of x, the linearization of x, and here we're going to represent it as P1 of x, a polynomial of degree 1, which is equals to f at a plus f dash at a into x minus a, right? So linearization is used to approximate the function at values near A, right? Not everywhere, near A. Now, if f has derivatives of higher order, suppose the second order derivative of for the function is also defined, in that case, you can define the quadratic approximation. Likewise, if third order derivative is also defined, you can go for the cubic approximation. So basically, in general, we can say that it has higher order polynomial approximations as well, one for each available derivative. And these polynomials, so this is a polynomial of degree 1. These polynomials are called Taylor polynomials of the function, right? So now we're going to define Taylor polynomials for the function, and you see that first P1x is basically this only, right? So let us see how the Taylor's polynomials are defined. Let f be a function with derivatives of order k, where k varies from 1 to capital N, in some interval containing A as an interior point, right? Then for any integer n from here I should write from 0 to capital N, the Taylor polynomial of order n generated by the function at this point represented by Pn of x is basically the same Taylor series, but now it is just chopped off after n terms, after nth order term, or you can say n plus 1 terms. So this is the same, we had this series where we had f at k order, fk at a upon k factorial multiplied by x minus a raised to the power k. Here k was varying from 1 to infinity. Now this is not infinity, this is number n, the order of the approximation. If you are going for the third order approximation, then you have p3 of x. In that case, you will have f third derivative and x minus a to the power 3. If you have second order approximation, you will go till f second derivative at a divided by 2 factorial into x minus a to the power 2, right? So this is how we define the Taylor's polynomial of order n. So we are defining the order of the polynomial, not the degree, right? So just as the linearization at x is equals to a provides the best linear approximation of the function in the neighborhood of a, the higher order Taylor polynomials provide the best polynomial approximation of the respective degrees. Okay, so basically this polynomial is going to be approximating this function at point A, right? So this polynomial will be very close to this function in the vicinity of this point, not otherwise, right? So you will be this polynomial hugging this function near this point A. Okay, so let's see an example. Let's just find the Taylor series and Taylor polynomials generated by this function at x is equals to 0. So what is the Taylor series? Taylor series will be this series. Summation k going from 0 to infinity, kth derivative of f at 0 by k factorial into x to the power k. Right? So you need to find the value of f at 0, then f first derivative at 0, all these values. So fx, f dash x, f nth derivative, it will be e to the power x. And when you find the function values at zeros, it will also be equals to 1, and hence you have this as the series. See, when you are writing series, don't forget to write these dots, that this is just going on. If you do not write this dots, means you are talking about the polynomial. Okay, so this is the Taylor series. Here you see we are going till infinity. So what is the conclusion? That the Taylor series generated by the function at point x is equal to 0 is this series, and since we have x is equal to 0, you know that Taylor series at point x is equal to 0 is nothing but the Maclaurin series. So the same question can be asked as if what is the Maclaurin series for e to the power x? In that case, it is not specified that at x is equal to 0, because Maclaurin series is defined only at x is equals to 0. And what about the Taylor's polynomial? In case of Taylor's polynomial, just remove this infinity by this number n. So this is a Taylor's polynomial of order n. And you can see that near this one, notice that this is e to the power x, this blue one. And then you see p1 of x is this straight line. p1 of x will be 1 plus x. p2 of x will be 1 plus x square by 2. And you see that they are in close agreement near the center. When you see here, these curves, the Taylor's polynomial of different orders, they are very much closer to the actual curve defined by y is equal to e to the power x. See next example. Find the Taylor series and the Taylor polynomials generated by the function fx is equal to cos x at x is equals to 0. So again, the Taylor series is given by this formula, right? So when you have this as a Taylor series, find the values of f0, f dash 0 and all the higher order derivatives. And we see fx is cos x and f dash x is minus sin x, f double dash x is minus cos x, f third derivative is sin x. And you can just say that in general, f2n, the 2nth order derivative of the function, is minus 1 raised to the power n into cos x, and 2n plus 1th order derivative is minus 1 raised to the power n plus 1 into sin x, right? And when you just substitute the value here, f at 2n of x, when you substitute 0, x is equal to 0, this term is going to contribute. And when you substitute here f at 2n plus 1 and at 2n plus 1 a derivative of f at 0, this will be 0 and this is not going to contribute, and you see these zeros coming here, right? All the odd power terms of x are 0 and you have only even power x to the power 2n, right? So we conclude that the Taylor series generated by cos x at x is equals to 0 is this series. Now we want to find the Taylor's polynomial. Now when you find the Taylor's polynomial of order 2n, it will be this one, right? You have to go till here, you have to go till 2n, right? Now what if you find the Taylor polynomial generated by this function of order 2n plus 1? In that case, you will go till one next term, and that one next term will be 0. So eventually you will be left with this term only. So in this case, since f at 2n plus 1 a derivative of f at 0 is 0, so polynomial of order 2n and polynomial of order 2n plus 1 will be the same, right? So here you need to notice that we speak of the Taylor polynomial of order n and not the degree, right? Because you see here order is 2n, here order is 2n plus 1, but degree is 2n, right? So we cannot say that if the polynomial is of degree order 2n plus 1, it should have degree also 2n plus 1. No, it could have degree lesser also. So we are defining the order and not the degree, because when you say degree, it means you are talking about this power of x, right? So polynomial, Taylor's polynomial for this function at this point of order 2n and order 2n plus 1, they are identical, right? So see these figures, you see that how well these polynomials approximate this function near 0. So this is p0 and p1 are just the same, p2 and p3 are just the same. Likewise, you can go till p18 and you see that they are in close agreement with the curve y is equals to cos x. Okay, yeah, that's it. With this, we are done with the unit 1 of the course. Thank you very much for lending me your ear. Have a nice day.